Okay, so for this video, we'll be talking about atoms, elements, and compounds, and the differences between these three terms. Now, first off, an element. It's a substance made of just one type of atom. And you can see I've put that word type in bold, or rather in caps. And that's because that word is super important. I've been an examiner for years on and off, and I've seen this question many times. What is an element? And a common answer is an element is a substance made of just one atom. Now I'm going to put my cursor before that period. I'm going to move the period across to separate it and say, if I look at that period, whatever it's made of, there's enough atoms in that period for everybody in the biggest crowd of people you can imagine to have, let's say, 10 million each. So imagine the Olympic Games, the opening ceremony, the sea of heads that you see if you look at the crowd. Soccer, the World Cup final. Again, so many people. The biggest rock concert there's ever been. So many people. Enough atoms in that single dot for everyone to have 10 million each. Honestly, they're even smaller than that. Okay. Now, so an element's made of just one type of atom, which tells me atoms can be different to each other. All of the elements, all the different elements that exist, are found in the periodic table, which, to be honest, that's not its proper title. It should be the periodic table of the elements. I'll find elements in the periodic table, I'll not find anything else. Two such elements are iron and sulfur, separate to each other, each one made of different types of atom. So that's an element, one type of atom. A mixture could be made of more than one substance, just simply mixed together. Doesn't matter how much of each. I could take my elements, iron and sulfur, and just mix them together. They're both solids, and that's a mixture. Now, there's still iron in there. There's still sulfur in there. I could get a magnet. Iron will be attracted to a magnet, sulfur will not, and I can get the iron away from the sulfur. A mixture keeps the properties of the substances it's made of. Air is a great example. Nitrogen, oxygen, helium, neon, krypton, argon, xenon, so many different gases, all mixed together. Compounds are different to elements. Compounds are made of different elements, but they are chemically bonded together. I'll do two separate videos on the nature of chemical bonding. I could have this compound iron sulfide. Oh, there are many codes in chemistry, but that IDE tells me two things are joined together, maybe sometimes more than two things. And a compound, one thing that's different between a compound and a mixture. Fe is iron, S is sulfur, chemical formula FeS. Tells me that for every iron atom, I've got one of sulfur. The ratio is 1 to 1. Same in any compound. There's a fixed ratio. All right, so water is H2O. It just happens that there's two hydrogens, H, for every oxygen. Carbon dioxide is kind of the other way around. Two oxygens for every carbon. So, element, made of just one type of atom. Mixture. Two different substances mixed together. They might be elements, they might not be. And it could be any amount of either. Compound. More than one element, but this time chemically bonded together. Now I'm going to hide this away for just a second. Let's put that in white font. And let me show you. Here I have the names of the three subatomic particles: proton, neutron, electron. Now, mass. If I were to take the mass of, let's say, a proton or a neutron, I wouldn't be able to fit it in that box. If I'm going to put it in grams, it would be 0.00000, and there'd be more than 20 zeros. I would lose count. I'd at least get bored. So to make things more accessible and more interesting and easier, we say the mass of a proton and a neutron are 1 AMU. AMU stands for atomic mass unit. I've written it out on the side of this slide here. Both of them weigh the same. Electron, incredibly light. We say, again, just to keep things easy, the mass of an electron, you know what? It's so light, let's just call it 0 and have done. Now, particles can have charge. They can be positive, they can be negative, they can be neutral. I've highlighted the little P standing for proton because protons are positively charged. Neutron, you can almost guess, a neutron is neutral, hence the name. Neutrons, neutral, and an electron, negative. So I've got three possible charges and they're all used up. Positive proton, neutral neutron, negative electron. Now I see my masses. The two that are, I'm going to use the word loosely, the two that are the heavier, proton and neutron, they have more mass. They're found in the nucleus, the center of an atom. And the electrons, being so much less mass, are found in orbitals. You can call them shells, you can call them energy levels, but they are orbitals. Three words means the same thing. Now, how are the electrons arranged? Periodic table's a crazy kind of shape, and there's always a reason. We have to, for IGCSE or for GCSE, go up to atomic number 20. Now, electrons, being negative, will always get as close to the positive nucleus where the protons are found as they can. And these energy levels, these shells, these orbitals, you choose whatever word sits best with you. 2 electrons can fit into the first innermost shell. And look at my periodic table. First row, H and He, only 2. So no need to remember that 2. You get a periodic table for paper 2 or paper 4, and it's there. 2 for the first row, 2 electrons in the first shell. Second shell, from Li, that's lithium, all the way across to Ne, that's neon, there are 8. 8 fit into the second shell, and 8 also fit into the third shell. Fourth shell, we only go up to calcium, number 20, Ca. But the fourth shell can hold some electrons for us, and that's it. Now, the number of occupied shells, these shells are just regions of space. They might contain electrons, they might not. If they are occupied, that gives us the row an element belongs to. That we call the period number. Period number is the horizontal row an element is found in. For example, helium, 2 electrons. Both electrons can go into the innermost shell. Electronic configuration of helium is just then 2. One number, first period. If I look at fluorine, F number 9 below, the 9 actually tells me that the proton number is 9. But I know number of protons is the same as the number of electrons, 9. Fluorine atoms have 9 electrons. 2 can fit in the first energy level or shell, 7 in the second. My electronic configuration, 2, 7. Two numbers, second period. Looking at the table, second row. One more, calcium number 20, biggest one we go to. Calcium 20, atomic number or proton number 20. 20 protons means 20 electrons. Look at the shape. 2 into the first energy level, 8 into the second, that's 10 taken care of. 8 more into the third, that's another 8 taken care of. 18, 2 left over. My electronic configuration of calcium then, 2, 8, 8, 2. 4 numbers, fourth period. Fourth period meaning the fourth row across. And you can see it belongs there. While we're here, group number tells us the number of electrons in the outside shell. So if I look, my second period, from lithium, Li, number 3, across to neon, Ne, number 10. Lithium will have electronic configuration 2, 1, and it's in the first column going down. We say the first group. Next to it, beryllium, 4 protons, 4 electrons. Electronic configuration 2, 2. The second column going down, we say the second group, 2 in the outside shell. One more, oxygen number 8, proton number 8. So electron number 8. 2 will go into the first shell, 8 will go into the second shell. 2 into the first shell, 6 into the second shell. That makes oxygen 6 in the outside shell. It's in my 6th column. We say the 6th group. So my periods are horizontal, rows going across. My groups are the vertical columns going down. And if I look at my elements, I've got the first 6 here. I've got my atomic number, number of protons. I've got my mass number. This would come straight from the periodic table. Atomic number gives us the number of protons. Number of protons is the same as the number of electrons. Number of neutrons, well, number of protons and neutrons together gives the mass number. So if my mass number, say for boron, is 11, 5 protons must mean 6 neutrons. I've already got 5 electrons because I know my 5 protons. Electronic configuration. Configuration, that name with figure in the middle, suggests number. And that's what it is. The number of electrons in each shell. So if I look at, say, boron, 5 electrons, 2 in the first shell, 3 in the second. My group number, if you remember, is the number of electrons in the outside shell, 3. My period number, how many shells contain electrons? 2 numbers, period 2. One more, helium. Proton number 2, 2 protons. 2 protons means 2 electrons. Mass number 4 means 4 protons and neutrons all together. I already know I have 2 protons, so I must have 2 neutrons. 2 electrons for helium. My electronic configuration is just that, 2. 2 electrons fit in the inside shell. We don't actually give helium a group number. It's in group 8 because it has a full outer shell, but that's unusual. Period number 1, only 1 shell occupied. And in this table, I will look at the elements one by one. I'll do oxygen first. They're there for a reason in this order. I see nitrogen atomic number 7, oxygen atomic number 8, miss a gap. Neon number 10. No prizes for guessing the atomic number of neon, 9. I want to look at these row by row now. We'll begin with oxygen because it's done. And I'd invite you to pause whenever I'm going to look at a row. Check it out for yourself. And then when I've done it, see if you agree. All right, so oxygen. Atomic number 8. 8 protons. 8 protons, 8 electrons. They're the same. Mass number 16. I already know I've got 8 protons, so 8 neutrons. Electronic configuration, all I'm going to do is to look at the number of electrons. 8. 2 in the first shell, 6 in the second. Now, group number. Group number is the number of electrons in the outside shell is, in this case, 6. Period number, how many shells? 2. 6 is my electronic configuration. That's 2 shells. That's period 2. I'll now look at nitrogen. I'll pause. So if I look at nitrogen, my atomic number 7 means my proton number is 7. If my proton number is 7, electron number is the same is 7. Also, my mass number gives me the total number of protons and neutrons. I already know 7 protons. I got 7 neutrons. Electronic configuration, well, I've got 7 electrons. 2 will go into the first shell, leaving 5 to go into the second. Group number, the same number as the number of electrons in the outside shell, 5. Period number, 2 shells have electrons in them, 2 in the first shell, 5 in the second. My period number is 2. Done. Now fluorine. Okay, so for fluorine, I've got my electronic configuration. I need to work everything out from that and the number of neutrons. If my electronic configuration is 2 and then 7, means I've got 9 electrons. If I've got 9 electrons, must have had 9 protons. If I've got 9 protons, my atomic number is 9. If my number of neutrons and protons altogether is 19, well, that's the mass number. Looking at fluorine, 7 in the outside shell gives me group number 7. And my period, 2 shells hold electrons, period 2. I could work everything out just from what I was given. Neon next. Alright, so neon atomic number 10 means 10 protons. That's what my atomic number tells me. 10 protons tells me I'll have the same number of electrons is 10. My mass number is 20. 20 protons and neutrons altogether. I already have 10 protons. I've got 10 neutrons. Electronic configuration. Okay, so there's 10 electrons overall. 2 will go into the first shell. 8 will go into the second. Group number. Number of electrons in the outside shell. Group number 8. And my period number. 2 occupied shells. Period number 2. Sodium next. All I've been given is the electronic configuration and the mass number. So if my electronic configuration is 281, straight off, I can tell you group 1, 1 in the outside shell. Period 2, 2 shells hold electrons. Sorry, period 3, correct myself. 281 is my electronic configuration. That's 3 numbers. Period 3. Number of electrons. Well, 281 can only mean 11 altogether. 2 plus 8 plus 1. 11 electrons means 11 protons. Now, if I know 11 protons, I mean my atomic number is 11. And my mass number, which was originally given, would be the total number of protons and neutrons, and so I must have 12 neutrons. On to magnesium. All right, so different information again. Group number 2 tells me 2 electrons in the outside shell. Period number 3 tells me 3 shells are occupied. If 3 shells are occupied and 2 in the outer shell, my full electronic configuration must be 282. 282 makes 12 altogether. That's 12 electrons. And 12 electrons means 12 protons in the nucleus. Atomic number is simply the number of protons in the nucleus is 12. And my mass number, total number of protons and neutrons, 12 plus 12, 24. Two more. Aluminium. All right, so I'm looking at what I'm given. Number of electrons, 13. I'm straight off going to say 283. There's my electronic configuration. If my electronic configuration is 283, my group number must be 3. Number in the outside shell. My period number also 3. 2, 8, 3. 3 occupied shells. Almost halfway there. If I've got 13 electrons, I must have 13 protons. They're always the same in an atom. 13 protons means my atomic number is 13. And mass number, total number of protons and neutrons, 13 plus 14, 27. Last. I'm looking at silicon. Electronic configuration again, 284, straight off, group 4. Number in the outside shell. Period number, 2, 8, 4, 3 occupied orbitals, period 3. Electronic configuration of 284 means I've used 14 electrons altogether, so electron number is 14. And A, the number of electrons is the number of protons. My mass number is 28. That's the total number of protons and neutrons. If I've got 14 protons already, I must have 14 neutrons. And finally, my atomic number, 14 protons, so my atomic number is 14. We're done. So you could be given different information about the atomic structure and work out anything. Moving on. As we had previously, number of electrons in the outside shell is the same as the group number. Number of occupied shells is the period number. Period number that we'll find an element in the periodic table. Now, almost at the end of this short video. Group 8. We've seen already that it contains helium. Even though helium only has 2 electrons in the outside shell, the big thing there is the outer shell is full. All of these elements have a full outer shell. And I know already the number of outer shell electrons equals the group number. Number of occupied shells is the period number. Now, one of the biggest rules in chemistry, I would say, the noble gases. Group 8. All have full outer shells. All are totally stable. There's a connection. If they're totally stable and they have a full outer shell, leads us to think that is the key to chemical bonding. They are stable because they have that full outer shell. Atoms of other elements will tend to try and get like the noble gases by gaining a full outer shell of electrons. And they can do that in two ways. They can do that by gaining or losing electrons, that's one way, transferring electrons if you like, or they can get it by sharing. And that will be the subject of my next two videos. On a separate point here, isotopes. Now, isotopes is one of those topics that's only dealt with once. You're never going to go back to it, not in chemistry. Touch on it very slightly, believe it or not, in physics, in the last physics module. And that, to me, signals danger. It's something that's easy to understand when you do it, but it's maybe not easy to understand a year plus later when you get tested on it. So what I plan to do at some point is to make a video with all of these messy little points that people get when they first do, and then they don't just get it, they forget it. But, okay, isotopes. Again, words, iso. Iso in front of a name tells me something straight off. The same. Isotopes are atoms of the same element, but they have different numbers of neutrons. Wow. So they've got the same number of protons, and that means the same number of electrons. The only way they can be different is to have different numbers of neutrons. Now, atoms of the same element must have the same number of protons. The difference, if they've got different numbers of neutrons, they must have different masses. The only property of neutrons that we're interested in is they have a mass of 1 AMU, 1 atomic mass unit. Now, chlorine in the periodic table is given a mass number of 35.5 and an atomic number of 17. Well, the atomic number of 17 tells me 17 protons in the nucleus. But wait, 35.5 is the total number of protons and neutrons. 35.5 subtract 17 for the protons already gives me 18.5. 18.5 neutrons? Impossible. You can't break these particles up. And the answer comes in the fact that chlorine has two isotopes. One has a mass of 35, the other has a mass of 37. So, the one with a mass of 35 got to have 17 protons, must have 17 plus 18 is 35, must have 18 neutrons. The one with a mass of 37, all right, I know I've got 17 protons, must be 20 neutrons. And 35.5 is the average number. 3 of the lighter isotopes of mass 35 for every 1 of the mass 37. Okay, so my symbols in the periodic table, two numbers. Be careful. Some periodic tables have carbon written as I've got it, 12 on top, 6 below. But in some it can be the other way around. Doesn't matter. We know that the small number, 6 in this case, gives me the number of protons, which is the same as the number of electrons. The big number is the total number of protons and neutrons. So in this case, 6 neutrons. There's no charge given to it. I don't see a plus or a minus as I do in the next box coming up. No charge must means my protons and electrons balance. 6 protons, 6 electrons. My last little box on this slide, chlorine, I see a negative charge. Chlorine. Atomic number 17, the small number, 17 protons. Large number, the mass number, 35. 17 protons already must be 18 neutrons. There we have it. I'm going to take this one here separately. The charge is negative. Electrons are negative, protons are positive. If my charge is negative, I've got 17 protons, must be 18 electrons. Now, these isotopes that we're looking at have exactly the same chemical properties because they've got the same number of electrons and therefore the same electronic configuration. The big deal, same number of electrons in the outside shell. Now, if you think about two atoms, they're going to collide. When they collide, what collides? It's the electrons in the outside shell. That's what matters. Protons and neutrons, they're not involved. They're in the center of the atom, long way away from the point of collision. And the only difference in different isotopes, they've got different numbers of neutrons. So, only the electrons are involved when atoms collide. The number of neutrons in the nucleus doesn't matter. I'm saying it's irrelevant. And electronic configuration's got to be the same if the atomic number is the same. Chemical properties of isotopes, they are identical. They have the same number of electrons, they've got the same atomic number. If they've got the same number of electrons, they'll be the same number in the outside shell. Need to gain or lose the same amount. Now, could be asked to calculate relative atomic mass. And to do that, look at how much of the isotopes we've got. Copper is Cu. There's two isotopes. A lighter one has mass 63. A heavy one has mass 65. The relative atomic mass will give me the average mass. Now, if I'm 69% of the lighter 63 isotope, I can get my total contribution to the final total mass by multiplying those together. Same for the heavier isotope. 31% abundance, and that must mean 31% abundance and the mass 65. Multiply those together. Add together the sum total of my masses comes to an average, divide by 100. I really am getting the average mass here. Gives me 63.48, which I'll round off, 63.5. Now, a couple of questions. I like to get my questions from IGCSE past papers, but I don't use the exact papers, but I do base these on them. Now, what I've got here, 4 elements, A, B, C, D, number of neutrons, electronic structure. Don't be put off by words. I personally would always say electronic configuration. Electronic structure means the same thing. 4 little questions. I'll pause, give you a chance to look at A, then I'll do A. Then B, C, D, and then the video's done. A. Which 2 elements are from the same period? Well, if you remember that my periods contain elements which have the same number of occupied shells. I could go for a number of options here. B and C and D all have electronic structure involving 3 occupied shells. If I'm going to choose 2 from the same period, I'm going to choose B and C, or B and D, or C and D. That's one point. My explanation is what we'll get the second point. They have the same number of occupied orbitals. Second question, which 2 elements are from the same group? 1 point. Explain your answer. Second point. And if we remember, the group number tells us the number of electrons in the outside shell. I look at A, 6 in the outside shell. I look at D, 6 in the outside shell. Both are in group 6, and my explanation for them being in the same group, same number of electrons in the outside shell. Atomic number of element C. Okay, no mention of protons here. But I can see 13 electrons, which tells me 13 protons. Atomic number is the number of protons, is 13. Done. And the last one. How many compounds are formed by element B? Well, if I look at B, 8 electrons in the outside shell. That makes it a noble gas. They don't form any compounds. And so my one and only answer is 0. That's the video over. Of course, the beauty of these things is you can go back and review any aspect of that you want. Thank you very much. I will leave it at there for this topic.